Hello, and welcome back to Geology 234 Intro to Remote Sensing. Today's lecture will include image classification. So, for the agenda for today, let's take a look at this. We're going to look at understanding remote sensing imagery, the fundamentals of image classification techniques, supervised versus unsupervised, remote sensing workflow and applications for image classification, and then any challenges and future directions of image classification. Remote sensing imagery refers to the visual representations of the Earth's surface or other celestial bodies captured by sensors onboard satellites, aircraft, drones, or other remote sensing platforms. These images are acquired without direct physical contact with the objects or areas being observed, allowing for large-scale data collection and analysis over extensive geographic areas. So that's a little bit of a review, since we do know the definition of remote sensing imagery. But we're going to briefly discuss the various types of sensors because that's important to understand in order to grasp image classification. Remote sensing imagery comes in various forms, including multispectral, hyperspectral, and synthetic aperture radar, SAR, data, each capturing different aspects of the electromagnetic spectrum. Remote sensing imagery can be obtained through various types of sensors, each capturing different aspects of the electromagnetic spectrum, including optical sensors. So these sensors capture electromagnetic radiation in the visible, near-infrared, and shortwave infrared portions of the spectrum. They are commonly used for capturing detailed surface features such as vegetation, land cover, and urban infrastructure. And then another sensor, and I'm kind of going down the right on this slide with a little more detail, are thermal sensors. These sensors detect thermal, infrared radiation emitted by objects. They're useful for applications such as monitoring temperature variations on the Earth's surface, detecting heat anomalies, and assessing thermal properties of material. Radar, radio detection and ranging sensors, that's another type of sensor. So radar sensors emit microwave signals towards the Earth's surface and measure the strength and time delay of the reflected signals. They are particularly valuable for imaging through clouds, vegetation, and at night, making them suitable for applications such as terrain mapping, vegetation monitoring, and flood mapping. LiDAR, light detection and ranging sensors, and we haven't really talked about LiDAR too much, but and we'll get into those to LiDAR data and sensors within the next few weeks, but LiDAR systems emit laser pulses towards the Earth's surface and measure the time taken for those pulses to return, so providing highly accurate 3D information about the terrain and surface features. LiDAR data is commonly used for creating digital elevation models, DEMs, mapping vegetation structure, and urban planning. Image classification is a fundamental technique in remote sensing. That involves categorizing pixels or objects within remotely sensed imagery into predefined classes or land cover types. So most remote sensing applications process digital images to extract spectral signatures at each pixel and use them to divide the image in groups of similar pixels, segmentation, otherwise known as, using different approaches. So spectral signatures, these are unique spectral reflectance patterns of different land cover types. So the role of feature extraction is identifying relevant spectral bands or indices for classification. And the importance of spatial context is that considering spatial relationships between neighboring pixels for accurate classification. So remember that satellites record the surface reflectance in different spectral bands and produce multi-band grayscale images. Thus, if we look at a single image pixel and plot its values stored in all the multi-band images spectral bands, we approximate its continuous spectral signature with a polyline, or a line made of segments. So remember to use only atmospherically correct images for something like this. Multispectral satellites images capture both the sunlight reflected by the Earth's surface and the light scattered by the atmosphere. However, when monitoring the environment, atmospheric scattering is a noise that must be removed before image manipulation or analysis, which is why atmospherically corrected images are important. So on the top is a multispectral satellite image, and the bottom is the spectral signatures extracted from that satellite image. How similar are the water, sand, and vegetation spectral signatures? Unfortunately, it is hard to tell how close they really are. To compare these spectral signatures, one can build a reference system made of orthogonal axes that reproduce reflectance in each spectral band. This reference system is called feature space and has one axis for each spectral band. In the feature space, the spectral signatures become points. Now, it's simple to calculate the spectral signature's similarity. The closer the points are, the more they are similar, which is what you see in the bottom right, where I'm pointing to in the text says spectral signatures plotted in feature space. So this is how you can compare bands 2, 3, and 4. Now it's simple to calculate the spectral signature's similarity. The closer the points are, the more they are similar. The Euclidean distance d is often used, which is this equation on the lower right on this slide. And that shows the formula for 2 points, points 1 and 2, in 3D feature space. And so where 1 is the first spectral signature, 2 is the second spectral signature, X is the axis for the spectral band 1, Y is the axis for the spectral band 2, and Z is the axis for the spectral band 3. I'm not expecting you to know this for any midterm or final. It's just good background knowledge to have. Spectral signatures in the feature space. So spectral signatures, curves, are transformed into points, and then similar spectral signatures are points close to each other. And then image pixels with similar spectral signatures are grouped into a cluster called spectral class. A spectral index is a math expression applied to a multispectral image to highlight specific properties of different land covers, their state of alteration, amount, or health. Spectral indices combine the reflectance information from one multiple spectral bands into one numeric value. They turn satellite images from a qualitative visual inspection tool into a quantitative numerical analysis tool. So look at the spectral signature of a vegetated image pixel. The gap between the low reflectance in the red band, due to chlorophylls, and the high reflectance in the near-infrared band, due to internal leaf structure, is an indicator of the greenness of the biosphere. And you can see that difference here on this chart on the slide. The more vigor the vegetation is, or the more green biomass is present, the larger this gap is in the graph on this slide. So thus, the difference between near-infrared and red reflectances is used as a proxy for overall amount and health of green vegetation. So how does it all relate? Well, mapping land cover from multi or hyperspectral imagery can proceed only on the premise that the target cover types are spectrally different from one another. So classification is a process of grouping pixels of similar spectral properties into spectral classes, in which each class is assumed to or designed to correspond to a surface cover type. So a number of factors can influence the spectral separability of target features. So the difference in ground observation, yet not distinguished from one another in the imagery. So the target features are smaller than the ground resolution distance, pixel size, and hence the pure spectra are commingled with spectra from other surface materials. The spectral signature of the target is overwhelmed by the spectral return from other very bright background or adjacent features. And then the actual variability of the spectral signatures in a particular target class in an image is greater than the spectral difference between classes. Field conditions such as atmospheric effects excessively modify the observed spectra. So the traditional approaches to image classification include handcrafted features, methods like histogram of oriented gradients, HOG, scale invariant feature transform, and a local binary pattern. Some classifiers support vector machines, k-nearest neighbors, decision trees, etc. Those are some examples. Okay, in an unsupervised classification, the spectral variance displayed by the features in the image is partitioned into a specified number of spectral classes without using prior knowledge of the existing cover types of their spectral properties. So the partitioned classes must then be identified and labeled by the analyst. Conversely, in a supervised classification, the analyst previously identifies certain pure examples of each target land cover, which can be delimited on the ground and identified in the image. So the spectral signature of each such target training site, quote unquote, is determined from the image and used as a starting point for aggregating pixels, which we have similar spectral characteristics for. We applied both approaches to classifying these data in order to compare their effectiveness. So these are some more methods of classification. Image classification involves assigning a label or class to a digital image, right? So for example, the drone image on the left, in this image on the left, below is a crowd at a festival, so it might be labeled as crowd. And the digital photo on the right might be labeled as cat or kitten. This type of classification is also known as object classification or image recognition. It can be used in GIS to categorize features in an image. And so there are machine learning tools that have been a core component of spatial analysts in GIS for decades. You've been able to use machine learning in ArcGIS to perform image classification, enrich data with clustering, or model spatial relationships. So machine learning is a branch of AI in which structured data is processed with an algorithm to solve a problem. Traditional structured data requires a person to label the data, which may be something you've done as well, such as a picture of cats and dogs, so that specific feature for each animal type can be understood within the algorithm and used to identify these animals in other pictures. Or you have the deep learning, or this is the machine learning, is a subset of machine learning that uses several layers of algorithms in the form of neural networks. And so input data is analyzed through different layers of this network, with each layer defining specific features and patterns in the data. For example, if you want to identify features such as buildings and roads, the deep learning model can be trained with images of different buildings and roads, processing the images through layers within the neural network, and then finding the identifiers required to classify a building or road. So there are many computer vision tasks that can be accomplished with deep learning neural networks. Esri has developed tools. Developed tools that allow you to perform image classification, object detection, semantic segmentation, and instance segmentation. Unlike supervised or unsupervised classification, object-based classification is not based solely on the analysis of spectral characteristics of individual pixels. That is, these per-pixel procedures generally use spectrally based decision logic that is applied to each pixel in an image individually and in isolation. In contrast, object-based classifiers use both spectral and spatial patterns for image classification. This is a two-step process involving segmentation of the imagery into discrete objects, followed by classification of those objects. The basic assumption is that the image being classified is made up of relatively homogeneous patches that are larger in size than individual pixels. This approach is similar to human visual interpretation of digital image, which works at multiple scales simultaneously and uses color, shape, size, texture, pattern, and context information to group pixels into meaningful objects. So I know there's kind of a lot going on in this slide, but this is an important slide, especially for this week's midterm. But semantic segmentation occurs when each pixel in an image is classified as belonging to a class. For example, in the image on the right, road pixels are classified separately from non-road pixels. On the right, pixels that make up a cat in a photo are classified as cat, while the other pixels in the image belong to other classes. In GIS, this is often referred to as pixel classification, image segmentation, or image classification. It is often used to create land use classification maps. So instance segmentation is a more precise object detection method in which the boundary of each object instance is drawn. So for example, in the image on the right, the roofs of the houses are detected, including the precise outline of the roof shape. And on the right, cars are detected, and you could see the distinct shape of the cars. This type of deep learning application is also known as object segmentation. And then we have panoptic segmentation, which combines both semantic segmentation and instance segmentation. For example, the image of cars, people, shows all the pixels are classified, and each unique object, such as each car, is its own unique object. And then we have image translation. So the image translation is the task of translating an image from one possible representation or style of the scene to another, such as noise reduction or super resolution. For example, the image on the slide shows the original low resolution image. Right here on the right shows the low resolution, and then the image just next to it on the right is the result of using a super resolution model. So this type of deep learning application is also known as image-to-image translation. And then we have change detection. So this is a deep learning task that can detect change in features of interest between two dates and then generate a logical map of change. So this works for urban planning, for housing development. So this is the image on the lowest point of this slide. So you could see that the image on the left shows the houses, housing development, and then as you proceed to the right, the change detection deep learning task is actually detecting this developmental change. So from 5 years ago, started the development of the housing neighborhood, and then 5 years later, the middle image shows the same development, and then the image on the slide shows on the right shows the logical change map where new homes are in white. So it does that change detection for you. Instance segmentation is one of the most difficult image-based computer vision tasks. It combines elements of semantic segmentation, so pixel level classification, and object detection, so instance recognition. Essentially, at every pixel, we wish to classify not only the type of object or the background the pixel is part of, but also determine which instance the pixel is part of. In simple terms, deep learning is an add-on to develop human-like computers to solve real-world problems with its special brain-like neural network. To help develop these architectures, tech giants like Google, Facebook, and Uber have released various frameworks for the Python deep learning environment, making it easier to learn, build, and train and diversified neural networks. Some examples are PyTorch, which is a young framework with a stronger community movement, and it's more Python friendly. Tensor, which is a very powerful and mature deep learning library with strong visualization capabilities and several options for high-level model development. It has production-ready deployment options and support for mobile platforms. And some of the most popular deep learning methods are CNN and then RNN, which are architectures called artificial neural networks. So the steps in image classification workflow, the steps include, number one, pre-processing, which I discussed earlier is really important. So any radiometric correction, geometric correction, atmospheric correction, that all need to be done prior to analysis. And then you have feature selection, which is the step in choosing appropriate spectral, spatial, and temporal features for classification. And then you have training and validation, so splitting data sets, dividing data into training, validation, and test sets. And this step also includes model training, so training classifiers using labeled training data. And then finally, evaluation, assessing classification accuracy using validation and test data. So those are the major steps in the workflow. Applications of remote sensing image classification include land use and land cover mapping, environmental monitoring, so detecting deforestation, tracking land degradation. Then you can also use it in agriculture, so identifying crop types, monitoring crop health, and predicting yield. Also used in disaster management or emergency management, so mapping flood extent, healthcare, diagnosing diseases from medical images, and e-commerce, autonomous vehicles, and then also security. So it's used in a wide range of applications. Spectral variability, addressing variations in spectral signatures due to environmental conditions and sensor characteristics can be a challenge. Scale and resolution may also be a challenge and something to consider. So balancing spatial detail with computational complexity for large-scale analysis. And then integration with multi-source data. So combining data from different sensors could be difficult, and platforms for comprehensive analysis. And then also to consider are the advancements in machine learning. So how will this change image classification or advance the analysis? So incorporating deep learning techniques for improving classification accuracy and efficiency. Always something to consider. Image classification has come so far from traditional methods to deep learning approaches with continuous advancements continually underway. So thank you for your attention, and I hope you found this lecture insightful.